All right, welcome back to our next video. In this session, we will be working a key question for the topic structure and formula. So it's the year 2000 and we're working question number 7. So the question is in the description. Now the first question, it asks about the properties of compounds for in a homologous series. So in a homologous series, the compounds, they will have the same general formula, functional groups, similar chemical properties, right? Each member will differ by a CH2 group, each successive member. And the physical properties, they will increase as they go from one member to the next. So density, boiling point, melting point, those will increase. So this is the part A of question number 7. So that's pretty much straightforward. All right, so for this question, for part B of the question, so it's a combustion question, combustion analysis. So we have 10 cm cube of our hydrocarbon. So we have 10 cm cube of our hydrocarbon, and we react it with oxygen, right? And we know that if you react an hydrocarbon with oxygen in excess, you will get CO2 and water. All right, now in the question, it said that we use 10 cm cube of the hydrocarbon with 120 cm cube of oxygen. And after the reaction is completed, we have 100 cm cube of gases. Now remember, we are producing CO2, which is a gas, but not all of the oxygen is being used up in the reaction. So at the end, so you use 10 cm cube of your gaseous hydrocarbon P with 120 cm cube. At the end, we have 100 cm cube of gas. All right? The 100 cm cube, it represents CO2 and any unreacted oxygen. Now it says on treatment with KOH, it is reduced from 100 to 60. The KOH is used to absorb the CO2. So if you have 100 cm cube of gases after the reaction occurred between the hydrocarbon and oxygen, and we said that the 100 cm cube is a mixture of the unreacted oxygen and the CO2. So you treat it with KOH and the volume, it drops to 60. So the difference between 60 and 100, that is 40. So when you treat the 100 cm cube of gas with KOH, the volume decreased to 60. That means 40 cm cube of gas was removed. And remember, KOH is used to remove CO2. So if on treatment with KOH, the volume dropped from 100 to 60, that means 40 cm cube was removed. So the 40 cm cube is for CO2. That means in the reaction, 40 cm cube of CO2 was produced. So that means at the end of the reaction, 60 cm cube of oxygen remain. So this 60 cm cube is for oxygen. So you start out with 120 cm cube of oxygen, but 60 cm cube of it remain. So you start out with 120, but at the end of it, 60 cm cube remain. That means of the 120, 60 cm cube reacted with the hydrocarbon. So when you're answering this question, what we need to do is figure out what volume of oxygen was actually used or was actually reacted with the hydrocarbon and what volume of CO2 was produced. Right? So the question stated the 10 cm cube of the hydrocarbon, 120 cm cube of oxygen. At the end of the reaction, you have 100 cm cube of gases. That includes the CO2 that is produced and whatever oxygen was not reacted. On treatment with KOH, the remaining gases, which is 100 cm cube, it decreased to 60. So we know that we get 40 cm cube of CO2 and 60 oxygen did not react with the hydrocarbon. So it's the amount of oxygen gas that we start out with minus the amount that remained that will give you the amount that actually reacted. So it's the initial amount, which is 120. Or if you want to say the total is 120 minus what is unreacted or what is in excess or what is left over. Any amount to phrase it, it's the 120, but you start out with minus the 60 that remains. So 120 minus 60, that gives you 60. So that's the first thing that we need to do. All right, so once that is done, you put the 60 here. All right, so for this type of question, we get the volume of the reactants and the CO2. This is how you will set out your answer. So you will write the balance equation. So the objective of this is to find the molecular formula of hydrocarbon P. So we put it in the format CXH Y. So we are going to figure out what is X and what is Y. So X is representing the amount of carbon atoms in hydrocarbon P, and Y is representing the amount of hydrogen in hydrocarbon P. So at this point, we know that 10 cm cube of hydrocarbon P react with 60 cm cube of oxygen to produce 40 cm cube of CO2. Now, what we are going to do now is figure out the number of moles of each compound, right, based on these volumes. And so what we are going to do is simply compare these three numbers, right, and divide each of them by the highest number that can go into the three volumes. So the highest number that can go into the three of them is 10, with giving you a whole number. So 10 into each, right, because we want a whole number. So 10 into 10, that is 1. No, 60 divided by 10, that is 6. 40 divided by 10, that is 4. So what this is saying now is that 1 mole of our hydrocarbon reacted with 6 moles of oxygen to produce 4 moles of CO2. Now, if 1 mole of the hydrocarbon produces 4 moles of CO2, the source of carbon in CO2 is the hydrocarbon. So if 1 mole of the hydrocarbon reacts to produce 4 carbons, that means the amount of carbons in the hydrocarbon must be C4. And remember, if you have 1 mole, you don't need to put the 1, right? So 4 carbons are in our hydrocarbon. So once we figure out that, we're going to determine, we're going to balance oxygen. So on this side, you notice we have 6 moles of oxygen, or you can say 12 atoms of oxygen. All right? So we have 12 atoms of oxygen. 6 tools, 12. All right? In carbon over on this side, we have 4 times 2, that is, we have 8 atoms of oxygen here. Now, if we are balancing oxygen, if you have 12 oxygen on this side, that means we must also have 12 oxygen on this side. So if you already have 8 here, and you only have 1 atom of oxygen in water, 1 times 4 is 4. So you have 8 oxygen in CO2 in the 4 moles of CO2 plus 4 oxygen in the 4 moles of H2O. So that's a total of 12 oxygen atoms. So at this point, the oxygen atoms are balanced on both sides of the equation. 12 oxygen atoms on this side and 12 oxygen atoms on this side. Now, in balancing the oxygen in water, we change the amount of hydrogen present. So we're going to check the amount of hydrogen present now. So 4 times 2, that is 8. That means our hydrocarbon should have 8 hydrogen atoms. And so our hydrocarbon is E3. So the molecular formula of our hydrocarbon is C4H8. All right, so that is how you will calculate the molecular formula of the hydrocarbon. Right. Now, if you look at the question, again, the question is in the description. Right? So if you look at it, the question went on to say that P is an isomer of Q. Q on hydration produces 2 compounds with molecular formula C4H10O. One of these compounds undergo oxidation readily, and one of them resists oxidation. So we have compound P, which we now know is an alkene based on the molecular formula C4H8. If we hydrate alkene, we know that we're going to get alcohol. So it says we hydrate compound P, not P, sorry. It says P is an isomer of Q, Q on hydration. So Q is still an alkene, right? Because it's an isomer of P. So Q on hydration produces 2 compounds. So we know both of them are alcohols. One undergo oxidation readily, one resists oxidation. And then the first question was asked was to determine the molecular formula of compound P and its homologous series. So we know that it belongs to the alkene homologous series. The next question now says that we should name the displayed, we should name and draw the displayed formula of isomer Q. Name and draw the displayed formula of isomer Q and give 2 reasons for our answer. So we know that compound P is an alkene. So we're doing B. So in the description, we're doing B part 1, 7B. That's part 1, 1B. All right, so we're at 1B. So it says name and draw the displayed formula of compound P. So P is the alkene, C4H8. We don't know the structure of compound P, all right? But we know it can be butene or a branched isomer. So it could be but 1E, but 2E. All right, so let's draw them out. So C4H8 It could have been but 1E. It could have been but 2E. So it could have been but 1E. It could have been but 2E. It can be 2-methyl, 1-propene, and it's a prop-1E. So for C4H8, these are the three isomers of C4H8. 1-butene, 2-butene, 2-methyl, 1-propene, or prop-1E, whichever way I want to say it. Now it says Q is an isomer of P. That means one of these structure is compound Q. How are we going to figure out which one is compound Q? The reason how we're going to figure it out, it tells us that on hydration, compound Q produces two compounds with the molecular formula C4H10O. We know it's an alcohol. The important part in the statement is when it says that one undergo oxidation readily and one resists oxidation. We know tertiary alcohols is the one that resists oxidation. So there's your answer. There's the big hint. You should get a tertiary alcohol and a primary alcohol. Well, primary or secondary, because those can be easily oxidized, but not the tertiary alcohol. So the question now, of these three isomers, if you hydrate them, which one can give you a tertiary alcohol? So let's hydrate all of them. So in hydration, we're adding a water molecule. So you break the double bond, right? You put hydrogen on one carbon. So let me just create some space. So you break the double bond. That's the alcohol right there. And as we know, this would be a secondary alcohol because it only has one hydrogen attached. If we do but2ene, the double bond would have been here. So you break it, you put a hydrogen and the OH. All right? That's also a secondary alcohol. One hydrogen is attached. All right? So in both of these hydration, we are getting a secondary alcohol. None of them can give us a tertiary alcohol. To get a tertiary alcohol, we cannot have a hydrogen atom attached to the carbon with the OH group. We cannot have a hydrogen atom attached to the carbon with the OH group for it to be a tertiary alcohol. No hydrogen must be present on the carbon with the OH group. Now, if we hydrate this compound, and the OH group comes here, and the hydrogen goes there, this is a tertiary alcohol. Because the carbon with the OH group, it does not have any hydrogen. All right, only carbon atoms are attached. So isomer Q would have to be 2-methyl, 1-propene, because that's the only structure that can give you a tertiary alcohol. Now you must also be able to get a primary alcohol. When you hydrate the alkene, right, based on, if you remember Markovnikov's rule, this product would be the major product. So with Markovnikov's rule, you have the major product and the minor product. So this product is the major product. The minor product, because remember, the hydrogen would go to the carbon atom of the double bond that already has more hydrogens. So this carbon atom has less hydrogen. So let's just put it back. Double bond, no hydrogen. This one will have 2 hydrogens. So the hydrogen always goes to the carbon of the double bond with the more hydrogen. And so the OH would come here. So that's the major product. They told us that on hydration, compound Q produces two compounds. So the two compounds would be 2-methyl 2-propanol and all right, so these are the two compounds, 2-methyl 2-propanol and 2-methyl 1-propanol. Now the question, it did not ask us for these structures, it asked us to name and draw the displaced formula of isomer Q. So isomer Q is 2-methyl pro 1-ene. So that's the answer. All right. 2-methyl. This is our answer. All right. Always put on your hydrogens. Do not leave it out like this. All right. Always put on your hydrogens. So this is the answer. 2-methyl 1-propene. This is isomer Q. That's the structure of Q. Now the next question, and the reason, so it asks us for two reasons. Two reasons are, the first reason, how we know that this is the structure for Q is because one, we must get a tertiary alcohol. For us to get a tertiary alcohol, it must be a branched alkene. So that is where we draw a branched structure. One, we must get a tertiary alcohol. Two, it must be a branched alkene for us to get a tertiary alcohol. So that is why we could not go with the straight chain. Because remember the straight chain, it would have given us secondary alcohols, secondary and primary alcohols. So it had to be a branched alkene for us to get the tertiary alcohol. So that is how we know that this is supposed to be the structure. All right. Then the next question, it asks us to draw isomers for C4H10. So C4H10, we already have two of them on the board, which is 2-methyl 2-propanol and 2-methyl 1-propanol. So the next two isomers would be 2-butanol and 1-butanol. So these are the isomers of C4H10O. So we can get 1-butanol, 2-butanol, 2-methyl 1-propanol, and 2-methyl 2-propanol. So those are the isomers of that compound. And the final question asks us for reagents and conditions for the hydration of Q and oxidation of C4H10. So for the hydration of Q, so for hydration of alkenes, we know we use water, concentrated sulfuric acid, and heat, right? 170 degrees Celsius. So concentrated sulfuric acid, water, and heat. And to oxidize alcohols, so for the oxidation of alcohols, you can use KMnO4, that's potassium permanganate, acidified slash H plus, it means acidified. Or you can use acidified potassium dichromate. And of course, you will apply heat. So if you actually want to oxidize the alcohol to your aldehyde or carboxylic acid and collect it, we need heat. Right? So it's not like the test tube reaction where you just add a few drops of KMnO4 and look for the color change. If you actually want to oxidize your alcohol, a sample of your alcohol to the aldehyde or carboxylic acid, then you will need to apply heat. So these are the conditions. And that was question 7 from the 2000 course paper. And that's the end of this video. So remember, these questions are related to structure and formula. Well, not this part. The first part of it, about calculating the molecular formula, that comes under the topic, structure, and formulae. So isomerism and calculating empirical molecular formula, naming compounds, right? So these sets of videos that I will be doing will cover those topics. So that's the end of this video, and I will upload some more in the series. So this is the first one.